Okay, welcome to Chapter 12, Section 2 on gravity. So let's start right off looking at key ideas here, things that are important in the chapter. So how are weight and mass related? We just talked about mass in the last section. Why do objects fall to the ground when you drop them? And what is the relationship between free fall acceleration and mass? Not mass. Why does a projectile follow a curved path? Alright, so let's move through the bell ringer here. Weight and mass. How are weight and mass related? Well, weight is equal to mass times the free fall acceleration. So weight is a measure of the gravitational force exerted on an object. If you remember from section 1, we talked about Newton's second law, which is F equals ma. Weight, you see here, weight is equal to the mass. Okay, there's the mass part of it, times acceleration. So any mass times acceleration is a force. When it's free fall acceleration, that's what we consider gravitational force, because free fall acceleration is due to the gravity of Earth. So weight is equal to mass times free fall acceleration, or in this case W is equal to m times g. And remember, g is an acceleration, it's a representation of acceleration. So m times acceleration is equal to a force, that force being the force due to gravity, which we simply call weight, and we give it another symbol called W. But do remember, it's a force. Alright, so weight is measured in newtons, just like all other forces. Weight is different from mass, we just talked about that. Mass is a measure of the amount of matter in an object, but weight's the gravitational force an object experiences because of its mass. And the more massive an object is, the more force that's acting on it. Alright, so let's watch this little video and listen along here.
The mass of an object depends on the amount of matter the object contains. As long as the amount of matter remains constant, so does the mass of the object. The weight of an object depends on the force gravity exerts on it. Therefore, if the force of gravity on an object changes, so does its weight. The weight of an object depends on gravity. Changing an object's location will change its weight. For example, consider an astronaut who has a mass of 80 kilograms. On Earth, this astronaut weighs 784 newtons. But on the Moon's surface, where the force of gravity is only 1.6 meters per second squared, the astronaut weighs 131 newtons. The astronaut's mass, however, remains the same on Earth or the Moon.
Let's go back there.
Weight can be measured using a spring scale. The spring scale measures the force exerted on an object by gravity. The weight of an object is expressed in newtons. Mass is measured using a balance. A balance uses a comparative mass on a lever arm to determine the mass of an object. The mass of an object is expressed in kilograms.
Alright, so let's move along here. Law of universal gravitation. So why do objects fall to the ground when dropped? All objects in the universe attract each other through the force of gravity. So Newton's law of universal gravitation gives the size of the gravitational force between two objects. So you see here you have force F equals G, that's a gravitational constant, but it's the first mass times the second mass, so you have two masses involved, divided by the distance between them squared. So M1 and M2 are the masses of the two objects, D is the distance between the two. G is a constant, it's just a number that is always constant and it's always put in this equation. All matter is affected by gravity. Two objects, whether large or small, always have a gravitational force between them. So like you and the Earth both have a gravitational force. You both have mass, it's just your mass in comparison to the Earth is very, 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 very small. Alright, so when something is very large, like the Earth, the force is very easy to detect. So gravitational force increases as mass increases. That's why you don't see a whole bunch of people out bumping against each other or attracting each other toward them gravitationally, because their mass is relatively small, where the mass of the Earth is relatively large. Gravitational force decreases as distance decreases. As people move away from the Earth, the gravitational force pulling them toward the Earth decreases. Alright, so law of universal gravitation. You have two masses here. So gravitational force is weak between objects that have small masses. So you have, again, here the same kind of mass on the left, but you double the mass on the right. So because there's twice the mass, the gravitational force is stronger when that one's larger. But when you increase the distance between them, the gravitational force becomes less as the distance increases. Alright, so let's watch this little video here. Looks like got Newton maybe talking about the apple falling from the tree.
Sir Isaac Newton realized that the force of gravity makes a small object, like an apple, fall toward Earth because Earth and the object are attracted to one another. Only the apple appears to move, however, because Earth has so much more mass. In Newton's law of universal gravitation, he explains that all objects in the universe attract each other through gravitational force. The mass of the objects and the distance between them affects the size of the force. Newton's law states that the force of gravity depends on the product of the masses of the objects divided by the square of the distance between them. In other words, if two objects are moved twice as far apart, the gravitational attraction between them will decrease by a factor of 2 times 2, which equals 4. So, the gravitational attraction between two objects moved twice as far apart will be 4 times less.
Okay, so you've got, remember that F is equal to G times M1 times M2, the two masses multiplied together, divided by d squared, which is the distance between the two of them. So see, when you have large masses here, you got the moon and the Earth, the force of gravity between them is fairly strong because the masses are very large. Even though you have a large distance, the masses are extremely large. Now, one thing I want to point out here, you can see the force of gravity here between the two, and something that they didn't say but is stated here, you see the arrows are the same size, which means both of them feel the same force. The force that the Earth exerts on the moon exerts on the Earth. It's the same force. The difference is the moon is less massive than the Earth, so the moon will move more, or seem to move more, than the Earth will. Alright, so free fall. So what is the relationship between free fall acceleration and mass? In the absence of air resistance, all objects falling near the Earth's surface accelerate at the same rate regardless of their mass. So free fall is the motion of a body when only the force of gravity is acting on it. So let's watch this little video here, which is going to explain to us about what free fall is and how it accelerates.
A falling object accelerates at a constant rate due to the force of gravity. As the object falls, the velocity will increase at a constant rate. The free fall acceleration due to gravity, symbolized by the letter G, is 9.81 meters per second squared at the Earth's surface. If only the force of gravity is acting on the object, then the motion is known as free fall. Air resistance is a force that slows a falling object. That is why a falling object can only be in free fall if it is in a vacuum. If an object like a spacecraft is in free fall, the occupants inside will also be in free fall and appear to float.
Okay, I do want to go back on this video here, go back and stop it right here at the first. I do want you to notice on this free fall acceleration, the velocity of this ball right as it's dropped is 0 meters per second downward. So right here, as the instant it's dropped, it has no velocity down. In the first second here, the velocity increases to 9.8 meters per second downward. And that's what that 9.8 meters per second squared means, is that the velocity, or basically speed, of the object increases by 9.8 meters per second every second that goes by. So from the first second, so from 0 to 1 second here, you have it goes from 0 to 9.8 meters per second velocity wise. In the second second, which here, second, it goes from 9.8 to 19.6. So if you actually take 9.8, add another 9.8 because it goes another second, you get 19.6. So for the third second, you're going to add another 9.8. When you add that to 19.6, you get 29.4 meters per second. And then if you went another second, you would add another 9.8. So that free fall acceleration just means that every second that goes by, you're adding 9.8 meters per second of speed to the object as it's falling. Alright, continued on. So air resistance can balance weight. So air resistance, if somebody's falling toward the earth, there's air as it's trying to move through. The air is trying to stop it from moving through. So especially if you have a large surface area of something like a parachute here. In this case, the force of air pushing up on the parachute is equal to the force of gravity pulling the skydiver down. In this case, remember from chapter 11 that we can have two scenarios. You have balanced forces here, and in balanced forces you could either have an object at rest, which we know is not the case here. So here this skydiver would be in constant motion, or have a constant speed. So they would be falling now to the ground with constant speed instead of accelerating. Then you have something called terminal velocity. The constant velocity, which I just talked about there, of a falling object when the force of air resistance is equal in magnitude and opposite direction to the force of gravity. So once you reach this constant speed right here, either with the parachute or without, that's something called terminal velocity. Astronauts in orbit are constantly in free fall. They're going around the Earth. It's almost like they're trying to fall to Earth, but the Earth is round, so it keeps pulling them around. Projectile motion. So why does a projectile follow a curved path? Projectile motion has two components, a horizontal component and a vertical component. When those two motions are combined, they form a curved path. So projectile motion, the curved path that an object follows when thrown, launched, or otherwise projected near the surface of the Earth. And you've done that when you've thrown any kind of ball or kicked a ball or thrown something. It always kind of takes an arcing path and comes back and hits the ground or the floor. So projectile motion has a horizontal component. After you throw a ball, no horizontal forces are acting on the ball. So it keeps kind of going horizontally at the same speed that it was when it left your hand. So the component of the ball, velocity of the ball, is constant after that ball leaves your hand. But it's also got a vertical component, and when you throw that ball, gravity, which is a force, is pulling downward on it. So even if you throw it up, gravity is trying to pull it back down, and it does so kind of slowly, which gives that ball a vertical motion. It starts to move toward the Earth or down. So in the absence of air resistance, gravity on Earth pulls that object that are in projectile motion downward with the same acceleration, 9.8 meters per second squared, just as it pulls down all falling objects. So orbiting is basically projectile motion. Any spacecraft in orbit are in projectile motion. They're just going fast enough that they don't come back into the Earth unless they slow down and let the Earth pull them back in. So the shuttle moves forward at a constant speed. Its path would be straight if the Earth didn't exert a gravitational force, but it's in free fall because gravity is pulling it towards Earth. Its path would be straight down if it weren't traveling forward. So when the forward motion and the downward motion, or downward force and the forward motion, are combined, it gives you this arcing path. But since the Earth is curved, it just follows that curve all the way around. So when the forward motion combines with free fall, shuttle follows the curve of the Earth's surface. This is known as orbiting. Alright, so let's look at this visual concept here on projectile motion.
Projectile motion describes the motion of objects that are in free fall but have an initial horizontal velocity. Both balls are released at the same time and fall with the same downward acceleration. The initial horizontal velocity of the yellow ball does not affect its vertical displacement. As the ball leaves the pitcher's hand, it has a constant horizontal velocity. The force of gravity acts on the ball and accelerates it downward, causing its vertical velocity to increase. The two motions cause the ball to move in a curved path, known as a parabola. Air resistance changes the path of a projectile. When traveling through Earth's atmosphere, the projectile's path is not a parabola.
That's because the air is pushing on it, so it kind of hits the ground or curves a little sharper and doesn't follow a real trajectory.